Good afternoon. My name is Justin Botelho, and my project is titled Building Energy Optimization in Honolulu Using Aladdin and Solar Analysis. The main engineering problem I focused on was how to reduce building energy demand in Honolulu's warm climate, where strong sunlight throughout the year increases indoor heat gain and raises air conditioning use. In climates like Hawaii, cooling demand is often a much greater concern than heating demand. So the challenge is to find practical ways to lower that cooling load while also improving sustainability through energy-efficient design and renewable energy. To study this problem, I used Aladdin CAD and building energy simulation to model and test the building design. My work focused on how different design parameters affected performance, including roof and wall R values, window U values, rooftop solar panels, seasonal solar exposure, and tree placement for shading. By adjusting these values and comparing the energy results, I was able to see which changes were the most effective. This project also connected with the Ahupua'a of Palolo, where I currently live in the Kamiki area. I learned that Palolo was historically known for its rich soil and abundant water, which supported expensive lo'i kalo cultivation along Palolo Stream. I also learned about the mo'olelo of Maokiheau, a place associated with agriculture and healing that was dedicated to the Lono, the god of fertility, rain, and farming. The connection helped me see this project was not only as an engineering study, but as a part of a longer history of land stewardship and sustainability in Hawaii. For this design portion of this project, I created a building model in Aladdin and improved it step by step. Instead of changing everything at once, I changed one major variable at a time, then compared the energy results before making the next improvement. This included testing roof and wall insulation, window performance, rooftop solar coverage, and the effect of trees. This step-by-step process made it easier to identify which design choices had the greatest impact on the building performance. To test this prototype, I used Aladdin's daily and yearly building energy analysis. Seasonal testing showed that cooling demand increased from 15.7 kilowatt hours in March to 24.9 kilowatt hours in June and 25.2 kilowatt hours in September. Confirming that stronger solar exposure increased air conditioning demand, I then compared yearly energy performance after making building upgrades. The baseline model used was 7,219 kilowatt hours per year, and after improvements, the value dropped to 5,800 kilowatt hours. One important result was that the roof upgrade was alone saved 956 kilowatt hours, making it the most effective individual upgrade. I also tested rooftop solar panels. After adding solar panels, the building still used 5,601 kilowatt hours of AC energy, but it generated 88,172 kilowatt hours of solar energy. This showed that solar was very effective, although the system was likely oversized for practical use, of course. Another part of this project was studying the trees as a shading strategy. The results showed that tree placement and size mattered a lot. A tree only saved 6 kilowatt hours of building energy, but caused 5,358 kilowatt hours of solar loss because it shaded the panels too much. In contrast, multiple small trees saved 35 kilowatt hours while causing no solar loss, making them a much better design choice. Overall, this project showed that building performance in Honolulu can be improved through a combination of insulation upgrades, rooftop solar panels, and careful shading design. The most effective strategies were increasing roof and wall R values, improving window U values, and using multiple small trees to provide shade without reducing solar output. This work is significant because it shows how simulation can help engineers make informed data-driven design decisions for sustainable buildings in warm climates. It also connects to broader work in sustainable building design, where energy modeling, passive cooling strategies, and renewable energy systems are combined to move buildings closer to net zero performance. For future work, I would improve this design by optimizing solar panel coverage so that it better matches building demand, refining tree placement to balance shade and solar generation, and testing additional envelope changes that could further reduce cooling demand. And I would like to thank Dr. Hanai for his guidance, feedback, and support throughout this project. I also appreciate KCC College for providing the opportunity to explore sustainable building design through this work. Thank you.